General relativity and the Standard Model represent the highest peaks of scientific prediction. Yet, Einstein's equations rely on an unresolved compromise. Constants like the speed of light and gravity are inputs, not outputs. They are arbitrary numbers manually entered to match the real world. This tuning dial problem persists because modern physics assumes the universe operates on a smooth, continuous spacetime manifold. If the goal is total parameter exclusion, mathematics predicting these numbers rather than just adopting them, then this core assumption of a smooth manifold is the primary barrier. The unified dynamics framework officially moves past smooth fields, replacing them entirely with a discrete, pre-metric combinatorial topology. The foundational building block here is the K4 tetrahedral complex. This system is governed by the parameter exclusion rule.
The architecture operates purely on graph combinatorics, structurally forbidding the injection of any arbitrary continuous tuning scalars. To succeed, this framework must show that the speed of light, the gravitational constant, and particle masses are the unavoidable structural consequences of this discrete geometry. In the forward time causal unrolling map, the network evolves through a strictly ordered sequence of structural updates. Within this grammar, continuous time is replaced by the accumulated count of these causal state updates. Length is defined as the physical footprint of the topological boundary generated by those updates. This creates a rigid structural parity. The network cannot execute a temporal update without projecting a spatial boundary. Mathematically, this one-to-one relationship ensures that the kinematic constant is always exactly 1. In this architecture, the speed of light represents the immutable synchronization gear governing the expansion of the boundary space itself. To derive gravity, we look at protomass, unprojected topological burden trapped within the internal phase space of the K4 network. The fundamental capacity required to enclose this defect is defined by the graph as 7/192. The Klein-Basin map then projects this internal network out into the macroscopic, observable universe. This projection creates a chiral split, dividing the network into an outward-facing observable boundary and an inward-facing unobservable root. Because of this split, the geometry available to our observable universe is exactly 1/2 of the fundamental defect capacity. This locks the kinematic gravitational constant at 7/384. Within a discrete network, gravity emerges as the geometric capacity cost required to embed internal topological burden into an observable boundary layer. When the unified internal burden projects into the macroscopic limit, it naturally fractures along invariant graph symmetries. The triadic internal base of the graph corresponds to SU3 color symmetry, the foundation of the strong force. The two-state boundary involution generates the SU2 symmetry of weak isospin, and the global closure phase invariance results in the U1 hypercharge. The standard model gauge symmetries are the continuous macroscopic shadows of these discrete graph invariances. Continuous field theories struggle to explain why there are exactly 3 generations of matter, or why their mass ratios are so irregular. Unified dynamics addresses this through 2 combinatorial routing operators, the neutral seed and the heavy lift, which build mass by wrapping defects in geometric shielding. The first stable generation, the electron analog, is the direct expression of the neutral seed, valued at 43/7. Heavier generations, like the muon and tau, are created by recursively applying the heavy lift operator, which stacks new geometric layers around the seed. A 4th generation is mathematically forbidden. Attempting another lift forces the burden to exceed the 192-state local phase space, shattering the structure back to its base state. Mass hierarchies are rigid, mathematically locked combinatorial packing limits. General relativity mathematically breaks down at black hole singularities, where it encounters the problem of infinite density. In this framework, infinities are impossible. The boundary of space is quantized by the 7/384 area capacity limit. Substituting this discrete area quantum into the Bekenstein-Hawking entropy bound yields a strict boundary limit of 96/7. This capacity limit forces the universe to hit a hard data ceiling, preventing the formation of zero-volume singularities. quantum gravity may not require more complex fields, but rather an acknowledgement of this discrete combinatorial ceiling. To move from mathematics to science, the unified dynamics framework must offer a falsifiable physical prediction. The definitive test for a discrete horizon lies in the ringdowns of merging black holes. Because a discrete horizon acts as a partially reflective boundary, it should cause a 1.8% truncation in the amplitude of gravitational wave overtones, followed by structural echoes. Current detectors lack the signal-to-noise ratio required to resolve a deviation this small against the background noise. However, third-generation interferometers, like the Einstein telescope or Cosmic Explorer, are designed to cross the threshold required to detect this signature. The framework is now in a state of passive observational hold. When these next-generation detectors go live, they will either confirm the smooth manifold of our current models or capture the discrete integer architecture of the universe.